So this is the 12th session in the subject of digital communication, and we continue our study of baseband modulation. And in this session we are going to concentrate on what is called as Emery signaling, and we will also study the pulse amplitude modulation. This is what we are going to study in this session. So let us start. Let us start with the simple block diagram first. So this is our analog signal. Xt is the analog signal. This is given to the input of analog to digital converter, and the output is a number of bits. How many bits? It depends on the A to D converter, depends on the design. So it could be 6 bits out, 6-bit output, 8-bit output, 12-bit output, and so on. So this XCT is the binary output. Now in order that this can be transmitted on a transmission line, we need to modulate this. How do we modulate? We modulate the amplitude of a pulse. And how many pulses we use? It depends on what kind of modulation we are doing. If we are doing binary modulation, then each bit is coded by one waveform. So you'll have two possible waveform, one for 0 and one for 1. In general, instead of representing a single bit by one waveform, what we can do is we can combine two bits. That is, we can have combinations of 0 0 coded by one waveform, 0 1 coded by another waveform, and so on. So if we combine two bits and represent this combination by a waveform, the number of possible waveforms clearly will be 4. In general, when we say it is an Emery signal, M denotes the number of waveforms that you have got. So M is going to be an integer power of 2. So it can be 2 itself, binary, or it can be 4, it can be 8, and so on. Okay. So before looking at the circuit by which we'll be able to do this modulation, we look at the symbols used first. So if we consider A to D converter, then the number of quantization levels is denoted by the letter L, and the number of bits per sample are denoted by the letter I. So clearly, as we have studied, 2 raised to I is equal to L. Then for pulse modulator, let us say M is the number of possible waveforms or number of possible symbols in the symbol set, and K is the number of bits per symbol. In that case, M will be equal to 2 raised to K. Okay, so these are the symbols which are used. So we are now ready to study how to generate the pulse amplitude modulation signal. So for that, we'll take a specific case in which we'll say K is equal to 2, M is equal to 4. So this is a quaternary signal, M equal to 4. So this is the block diagram. You can see there are 4 inputs to this, represented by 4 symbols here: S1T, S2T, S3T, S4T, and there are 2 control bits. So the digital inputs are connected here. So since K is equal to 2, we have got only 2 control inputs. So when this is 0 0, then S1T is connected to the output. Understand that this is a multiplexer circuit, and based on the value of the input bits, either S1T goes to the output, or S2T, or S3T, or S4T. So if it is 0 0, then ST is equal to S1T. If it is 0 1, then ST will be equal to S2T, and so on. That is how a multiplexer functions. So in this case, we have shown this S1T, S2T, S3T, and S4T by different waveforms which have different amplitudes. So you can see S1T in this particular case has a smallest amplitude, then S2T, then S3T, and then S4T. So this gives you an idea of how the pulse amplitude modulated signal is generated. Okay. So let us discuss a possible scheme. S1T has an amplitude 0 volts. In general, you can have 4 different amplitudes. We are talking about a specific possible scheme in which we say that S1T has amplitude 0 volt, and this is basically coding a sequence of binary digits which is 0 0. S2T represents the pattern of binary digits which is 0 1. So S2T has amplitude of 1 volt and it represents 0 1. S3T has amplitude of 2 volts and it represents 1 1. Note that is 0 0 0 1 and then 1 1. The reason for this is whenever the signal is transmitted and received, because of noise there could be an error. So S1T may be confused with S2T. In that case there will be only 1 bit error in this case. So if 1 is confused with 2, again there is a 1 bit error. Now S4T has the amplitude of 3 volts and this is 1 0. Note again, if this is confused with this, there is only a 1 bit error. Understand that if instead of this assignment, suppose we had said 1 0 here and 1 1 here, then if 1 is confused with 2, then there is a 2 bit error. That is the reason this kind of assignment is done, and this is called as gray coding. Alright. So at the receiver, how do you decode? What you receive is S1T, which has an amplitude of 0 volt, or S2T, which has an amplitude of 1 volt, and so on. But because of the noise in the system, because of the distortion in the system, the amplitude that you detect may not be exactly equal to one of these fours. It will be somewhere in between. So you need some rules in order to make your decisions. So what you do, if signal is less than 0.5, so it's around 0, say it could be negative for some reason, then it goes up to 0.5 volts. You say 0, you decide that 0 0 was transmitted. If signal lies between 0.5 and 1.5, then you decide that 0 1 was transmitted. Then if it is between 1.5 and 2.5, 1 1 was transmitted. And finally, if it is greater than 2.5, you assume that you detect that 1 0 was transmitted. So this is one possible scheme. Okay. Now, in order to compare the performance of various signaling schemes, that is binary and quaternary, etc., we need certain parameters. So again, what we are going to do is to calculate the bandwidth required for, let us say, binary, and then we'll calculate the binary required for quaternary. So let us do the bandwidth calculation for binary signaling first. Let us say I is equal to 8 bits from ADC, and let's say k is equal to 1, m is equal to 2. That is what we mean by binary signaling. So we have only S1T and S2T in this particular case. Now to calculate the required bandwidth, we need to calculate the bit rate. So how do we calculate? Let's assume that our analog signal is a speech frequency signal. Its maximum frequency is 3.5 kilohertz and the sampling frequency has to be at least 2 times this. So it has to be greater than 7 and let's say 8 kilohertz, which is a typical sampling frequency used. In that case, the PCM bit rate, 8 bits per sample, multiplied by the sampling frequency, that is 8 kilohertz. So understand, this PCM bit rate is assuming 8 bits per sample and assuming sampling frequency of 8 kilohertz, we get R equal to 64 kilobits per second. Now, when you code this by a waveform, let us assume that we have a full width pulse that is non-return to 0. In that case, the bandwidth requirement is same as R itself, which is 64 kilohertz. Okay, so that is the bandwidth requirement for binary signaling. Let us now obtain the bandwidth requirement for quaternary signaling. So again, initial calculations are similar. I equal to 8 bits from ADC, but now k equal to 2 and m is equal to 4. So 4 waveforms, that is why quaternary signaling. Then initial calculation, as we said, calculating the bit rate is similar because sampling frequency is still 8 kilohertz and this is 8 bits from ADC. So your bit rate is R equal to 64 kilobits per second. But now what you are doing, you are grouping 2 bits and then coding. So you have to wait for 2-bit time before you code the symbol. So therefore the symbol rate itself is 64 divided by 2 equal to 32 kilosymbols per second. And again, if we use the full width pulse, then the bandwidth requirement is 32 kilohertz. So note that if we are using a quaternary signaling, the bandwidth requirement is half that of binary signaling. Okay. Now, there is often a philosophy in the digital communications or communications in general, that is trade-off of power and bandwidth. You will find for in order to control the noise performance, you have two resources available with you. Either power, increase the in transmitted power so that the received power is more and your noise performance will improve. Or another resource is bandwidth. By employing larger bandwidth, it will be possible for you uh, to reduce the power. So this is called as a trade-off of power and bandwidth. So what we are going to do is to compare binary and quaternary signaling and see how this trade-off works. So we compare two cases. K equal to 1, binary signaling, we have already seen bandwidth is equal to 64 kilohertz. And ST is either 0, it represents 0 or 1. For quaternary signaling, K is equal to 2, and we have seen bandwidth is 32 kilohertz, half of this bandwidth, and ST has amplitudes of 0, 1, 2, 3. Here ST had amplitude of 0 and 1. So the difference between the consecutive levels is same. Note this is 0 and 1. So the difference is 1. Here 0, 1. Again the difference is 1. Between 1 and 2 again the difference is 1. Between 2 and 3 the difference is 1. So because of that the noise performance is same as the difference in consecutive levels is same. However, in this case the maximum value of the voltage for ST is 1 volt. Whereas in the case of quaternary signaling, the maximum voltage is 3 volts. So what it means is, for binary you are using more bandwidth, 64 kilohertz compared to 32 kilohertz, but less power, Vmax is equal to 1. Whereas for emery signaling, for quaternary signaling, M equal to 4, less bandwidth, so that is 32 kilohertz, but more power because Vmax is equal to 3. So in this session we have discussed emery signaling in general, and we have talked about one significant aspect in the communications, that is trade-off of power and bandwidth. And time and again when we discuss various techniques, we'll come across this trade-off. But in this session we have talked about the pulse amplitude modulation and discussed the trade-off between power and bandwidth by comparing binary signaling with quaternary signaling. And that's all in this session.